Thank you all for being here after yesterday's adventures of being here bright and early. Thank you to the organizers for the honor of giving me the opportunity of talking to you. I would like to talk to you about the title of this talk is Free Quantum Computing, and I'll get into why I called it that in a minute. As Bart was saying, I've had the pleasure of working with a lot of people on this. Most of the first couple are at the University of Edinburgh. Pablo did his PhD and moved on to a company called Quantinuum. Kim is a current PhD student, and she actually made a little logo because the project is called Rubber Duck, DUQ, for Dynamic Universal Programming, quantum programming. But most of the work that I'll be talking about is with these people that I certainly cannot claim to lead. Okay, so free quantum computing. I'm going to do a talk in 4 parts. First part is going to be mostly propaganda. Then I'm going to talk about reversible classical computation. That's going to be our baseline. I'm going to try and build on that to get to all of quantum computing. And in the end, we'll do some equational reasoning and see why I think this is a useful way of doing it. So the motto for today is, I would like everything to be free. Free in 3 senses. First sort of shallow sense is I'm Dutch originally. We are known for being thrifty. My adopted country is Scotland, who are also known for being hawkish with their money. So everything should be free in that sense. But more seriously, in the second sense, free in the sense of liberation. I would like to, so currently quantum computers are programmed in a way that presupposes a lot of background knowledge on the part of the programmer. You can't just start doing this with a normal sort of CS curriculum education. I would like to free and liberate people to be able to do that. But the third way, the real free, I mean, is sort of in the categorical way, free in the sense of minimal extension. I want no accidents. I guess in the words of Radiohead, no alarms, no surprises, all the structure that's there should do its purpose and nothing else. So free in this sort of categorical sense. And when I said we're going to be building on classical reversible computing, that's what I mean. We're going to add sort of a free universal property to this to make it lift it up to quantum computing. But I'll start with the propaganda. And the first bit of propaganda is about notation. So I've written on the slides here, notation isn't just a way to write ideas. It sort of stimulates what kind of ideas you can have. So first case in point is Roman numerals. This is a great notation. You can use it to write down numbers and to some extent calculate with them. They're great for clocks and inscriptions, but they're a nightmare to compute with. Can you imagine sort of trying to prove the ABC conjecture or something with Roman numerals? I can't really. So these are not good for computation. We would like some sort of better notation if you're going to work seriously with numbers. A bit more seriously, notation, you could see it as a sort of embodiment of abstraction. If you choose the right notation, that will help you sort of think the right thoughts in the following sense. First, it's sort of scalable, and that's a real problem in quantum computation. We can do, we have tens of algorithms. They work on maybe hundreds of qubits that can live for thousands of clock ticks, and that's it. We need to sort of scale this up. So the way they're currently programmed is really sort of low level, and we'll see that in a minute with gates being clicked together, sort of assembly language. And we would like to really scale this up. So we need to be able to think bigger thoughts. We need the right kind of notation and abstractions to do that. Same kind of sense, it's a good kind of notation or good kind of programming language should make things automatable. You shouldn't be stuck in having to copy paste lots of boilerplate all the time. That should be taken care of by easy steps. And similarly, you want to be optimizable. If you have a big mass of gates that you can't see the forest for the trees, it's going to be very difficult to make this better, more efficient. And all of this you could capture in a sort of scientific way as making it more understandable in some sense. You have the right kind of notation or the right formalism, then you can think the right thoughts. You can understand better what's going on. So as a case in point, I have a bit of audience participation for you. Here's a waveform, an audio file, or a picture of, I guess, the amplitude graph of a piece of sound. Who can tell me what this piece of music is? It's a weird question, right? Can you at least tell me if this is happy or sad music? But you win the biscuit. So this is clearly the wrong kind of notation if you want to be a composer, say. So I'm going to write it down a different notation now. Who can now tell me what piece of music this is? And I know there's at least one person from Salzburg in the audience. So I'm not going to sing it, but this is Mozart's clarinet concerto. Many people will know it. I tried to pick something many people would know. And clearly this is much better notation if you're working with music. Can you imagine, if you are Mozart and all you have to work with is this kind of waveform, could you ever come up with that? I'm not saying he can't, but I would have problems. So we want the right kind of abstractions and notations is the point here. Now, still a bit sort of tongue-in-cheek, but going more seriously, this is what quantum computations look like. At the very top there is a quantum circuit. So it flows sort of left to right, qubits go into the left, follow the wires, and get acted on by gates like these H's and X's, and these, don't mind the notation too much, these are controlled NOT gates. And in fact, this is the quantum circuit for an algorithm called Grover's algorithm, which is one of the standard ones that has proven speedups over classical algorithms. This is bad. I don't like this. We can't really think in this way. It works fantastically well, but if you want to manipulate this and do some program transformation on it, it's a nightmare, just like the Roman numerals, just like the sound. And what's even worse, this is, for better or worse, the sort of standard language for quantum computation at the minute. But when you are taught this, typically from a physics kind of background, you have to know about matrices. So this top line, this quantum circuit, is kind of shorthand for, this is not the exact same matrix, but that's a crucial part of it, this 4x4 matrix over there. And I personally really cannot think at this kind of level of detail. I have no idea what's going on if you give me that matrix. So what would be better if you can write something like this? And this is something that we're working on, that one of the people on the front slide, two of them actually invented. This is also Grover's algorithm. And you can actually sort of see what's going on. At least I can, whereas I couldn't do that up there. So moral of the story, circuits bad, matrices worse, structure good. Let me back that up by another argument. I'm saying, I find this difficult to work with, but here's a more sort of evidence-based argument for that. This is notation for what's called a Toffoli gate, controlled NOT gate. So if you think about these as bits, if the first control bit is set and the second control bit is set, then the third bit is acted on by NOT gate, it's flipped. If either of these are not set, nothing happens. Controlled NOT. This is a 3-bit or 3-qubit operation. And in fact, I'm going to claim all existing quantum hardware today can only do 2-qubit things. So you have to compile this down into some native gates that they can actually execute. The typical way of doing that is this. Right? So there's still these are controlled NOTs. Right? So 2-qubit gates, some gates called T and some gates called H. Now, a nice property of this controlled NOT gate, this Toffoli gate, is that it commutes with Z measurements, as they're called. So you can first do this and then a Z measurement, or you can do it the other way around, and it doesn't matter. You get the same outcome, the same state at the end of the day. But if I give you this and I ask you, does that commute with a Z measurement? I think you'll be hard-pressed to find out, because each of the phases don't commute with a Z. It's really about the combination of all of them together. So these kinds of properties are totally obscured. So the question I want to try and answer in this presentation is, what makes a quantum quantum? We're going to start from a base level of, we know what classical computation is, right? There's no need to reinvent the wheel. Let's reuse all this infrastructure from classical computer science. What can we add to that to get some sort of platform where we can specify quantum computations? And the less we can add to it, the better it is for us, I think, because that really sort of specifies this is sort of where the advantage lies. More pragmatically, that means if we know sort of where this advantage lies in some sense, what is this extra free property we have to add, we can lift that into making programming language constructs. Right? And I'm probably sort of preaching to the choir here, but you cannot just reuse many classical programming constructs, like if then else doesn't work, while loops don't work, recursions don't work for sort of foundational reasons, and you have to find other things. And we're looking for the right kind of constructs. And I think if we investigate the semantics first, because we know exactly what the semantics are, and that from that sort of rederive some sort of syntax that works well. So that's what I'm going to try and answer today. But before we get into that, I have to make a caveat. When I say free and universal, I'm going to use universality in two senses of the word. First one is sometimes used by complexity theorists and computability people. A set of gates, for example, is universal when every computation you might want to do, you can express using that set of instructions. Right? So that's computationally universal. I immediately have to make a caveat to that, because in the classical world, gate sets are finite. You know, bit strings, there's finitely many of them. Everything is finite, so you can say that. In the quantum world, things are more continuous. And in fact, there's an uncountable number of states. So there's no way any finite gate set can ever be computationally universal in that sense. So we have to say sort of approximately universally computational, in the sense that I have a finite gate set. I have some specified error margin that you can give me, some epsilon. This set is going to be approximately computationally universal when every computation you might want to write, you can express as a circuit up to epsilon. Okay, so that's the first sense of universal. Second sense of universal, I hope you all know, but let me remind you anyway, is the categorical property that, you know, says this is sort of the free or the minimal thing you can build with that property. The first cases where you see this in a normal kind of education, if you're coming from a math background, might be tensor products, which is this property over here. If you have two vector spaces V and W, you can talk about bilinear maps to a third one. There's a thing called a tensor product that the Cartesian product injects into, and it sort of makes bilinear maps linear. It's sort of the smallest thing such that bilinear maps turn into linear maps. Or if you're coming from a computer science background, maybe the first time you saw a universal property like this is with exponential types or function types. And they're in the same kind of universal way. The smallest set of functions from Y to Z that support an evaluation procedure. Smallest in the sense that if you have any other thing that pretends to be an exponential type, a function type, then it sort of must factor through the universal one. Okay, so part two, I'm going to talk about classical reversible computing. And this is a good baseline because most of quantum computing is reversible in the sense that the laws of nature are, you can sort of run them back and forward, and this happens for computations too. You sort of do lots of reversible steps, and at the very end of the day, you ask, you know, what is the value of this qubit? These are called measurements. I'm not going to talk about that today. We can take them into account in the story, but to keep it simple, I'm not going to talk about that. So only the reversible part is sort of where you could say is where the computation happens. So if I'm going to build on something we know, it should be reversible classical computation. So let's start there. I'm not sure how much you all know about this, so I'll start fairly low level. This is something, reversible classical computation has been something that has been around since at least the 1970s, 80s. And the idea is every step in the computation, I should be able to reverse. Here's a nice model for this that I kind of like. It's called billiard ball computing. It was sort of invented, I guess, by Fredkin and Toffoli, two of the main inventors of this, people that worked a lot on reversible classical computing. And the idea is this: I have here a billiard table of a funny shape. It's almost square, but it has some cut off edges. It has some pockets. I'm going to think of these pockets as inputs and these pockets as outputs. So a bit goes in, kind of. I can put a ball in here, I can roll it in here, or I cannot, right? That's like a 0 or a 1. So it has 2 inputs, 3 outputs. What happens if I put a ball in here and none in there? We're assuming everything is perfect, there's no friction, etc. Ball will just roll straight through and go to the, so this output bit will be 1. Right? Same, if I put in a ball here, but no ball there, it will roll straight through, you can get something here. If I put no balls in, no balls will come out. But the interesting case is if I set this bit, if I roll in a ball here and I set that bit, I roll in a ball there, then there'll be a collision here. And we're assuming everything is perfect. So, you know, they will bounce off at exactly right angles. This one will go here. It will bounce off this piece, go there. This one will go here, bounce off that little angle, go here. They will collide again. So one of them will come out here. The other one will come out here. Right? So this output bit will be set exactly if and only if both of the input bits were set. So this computes in a reversible way, the AND function. I say reversible because I could roll the balls backward and the same thing would happen. This is not just some frivolous model. This is a computationally universal model. If I had you know, an infinite supply of billiard balls and an infinite warehouse with enough felt to make it any table of shape I want, I can make any bijective function implement like this. For a long time, this was sort of theoretical, but actually nowadays, there's startups wanting to build chips that are reversible because they sort of take less energy, and machine learning, this is an important thing. So this is getting more interesting. So that's reversible classical computation. And we're going to think about this in a slightly different way. We're going to model this, and now we're starting to get serious, as a rig category. Now, everybody knows what a category is, of course. Hopefully, everybody knows what a monoidal category is. So, sorry, let me go a bit slower. So a category, you have objects, right, A and B, and you have function morphisms that go from A to B. You can compose them. There's a function that does nothing, a morphism that does nothing. That's what this law says, and you have composition is strictly associative. That's nothing new. Monoidal categories, you can compose functions in a different way. If you have two morphisms of arbitrary type, one from A to B, one from A prime to B prime, you can put them together sort of side by side. You can make a new morphism that's called F tensor F prime that goes from A tensor A prime to B tensor B prime. And this is also, this putting together of things side by side also satisfies some laws. It has to be associative up to isomorphism. There's a special object called 1 or I that plays the role of doing nothing. And I'm going to be interested in systems where A tensor B is iso to B tensor A. Importantly, these sort of isomorphisms have to satisfy some coherence conditions, but let's forget about that. Okay, so this is category. You can draw that in the string diagram calculus like this. First do F, then do G. For monoidal categories, you can draw this in a string diagram calculus as doing F while doing G, sort of side by side. And this braiding or symmetry tells you I can swap strings around like that. For a rig category, there's a second way you can put, a third way you can put morphisms together, which is a second monoidal structure that I'm going to write as O plus. It has all the same things as we had before, except now I'm going to call it plus, and I'm going to unit object O or 0. And you should think about natural numbers. So objects are something like natural numbers. You can sort of add them together. You can multiply them together. You can add them together. And there's morphisms between them. And the crucial thing about a rig category is these two monoidal structures have to cooperate with each other in this kind of way. I want the times to distribute over the plus. In other words, I want it to be a canonical natural isomorphism between these two objects, these two types for all ABC. And I want 0 to be absorbing in this kind of sense. And just like before, these have to satisfy, in this case, 24 coherence conditions to make sure that all the bookkeeping stays straight. So that's a rig category. The standard example you could think about is finite sets and functions, for example. So, you know, function composition is a category. You can take Cartesian product of sets. And then if you have functions between sets, you can get a Cartesian product of functions. And you can take disjoint union of sets. And if you have two sets and you disjoint union them and functions out of them, you can get a function between the disjoint unions. And indeed, sets behave like this. Or you could even take sets and bijections, same thing. Okay, so that's rig categories. Everybody happy with that? So rig categories, I'm going to claim, are a good language to talk about permutations or bijections between finite sets. So here is a 4-element set, consists of 4 colored balls, orange, green, blue, red. And I'm drawing this sort of little diagram to indicate a function that sends the red to blue, that sends green to red, orange to blue, green to red, blue to orange, and red to green, right? You can draw all functions that way. It's a permutation because I could do this in reverse. Or you can think about this, if you like, as a 4x4 matrix with only zeros and ones, like a permutation matrix. Each row and column only has one non-zero entry. That's a permutation, fine. And I claim permutations give semantics for classical reversible programs. This is what I've been building up to all the time. If you have some sort of classical bijection between functions that I want to implement, I can write that down as a permutation like this. I can compose these things, right? If I have So this, if I have this permutation over there and I can compose it with itself, I happen to get that one because orange goes first to green, but then to blue. Orange goes to blue, green goes to blue, goes to red, etc. So this one shifts by 1 each time. You can also shift by 2 if you compose them. Turning it around, that means that this permutation here has a square root. Right? I can write this permutation as the square as doing 2 times some other permutation. For some permutations, I can do that. But for other permutations, you cannot. For example, here's a 2-element set. If you only take the orange and the green, and I swap the 2, there's no way I can take a square root of this. There's no permutation on a 2-element set that if I do it twice, I get the swap map. So in some sense, this is missing from classical reversible computation. If you think in terms of matrices, that means that if you take some polynomial in this matrix ring, not every polynomial will have a root. And to take this even more seriously, because we like type theory, we like programming languages, you can make a programming language out of this. This is called Pi, capital Pi for permutations. It's a combinator language that looks like this. It's strongly typed. You have some value types like 0 and 1, and I want to be able to add 2 types and multiply 2 types. Terms are going to be like bidirectional things. I want to run them forward and backward. I have all these isomorphism that we were talking about. These kinds of things are terms in the language, things you can do, instructions you can give the computer. That's all these things. And I want to be able to like concatenate commands, just like we did for types, right? Just like we did in a rig category. So for example, the type of, let's say, this is an interesting one, the distributor, I guess, is something that takes a product type where one of the factors is a sum type and turns it into a sum of products, just like you would expect for natural numbers. And then there's formation rules. And this is a programming language. It's some sort of syntax. You can write programs in this way. You can give semantics to these kinds of programs in rig categories, because each of these commands I can obviously interpret as the corresponding thing in a rig category. So think of it as sets and permutations, if you like. And in fact, finite sets and permutations forms the initial rig category. Right? So any rig category whatsoever, there will be a function from finite sets and permutations to it, and a unique one. So this is sort of the smallest programming language you can make about permutations, about classical reversible computing. This is the free universal one. And you can program kind of interesting things in here. I've written some down here. So let's look at this. If we have any program C, I can make a controlled version of it, which takes an extra bit. If that bit is set, I'm going to do C. If that bit is not set, I'm not going to do anything. So how do you do it? You start with, let's say, C goes from bits to bits. So this is a 2-bit to 2-bit thing. First, I'm going to do dist. And I'm going to think about bits as, where do we go? This type 1. And 1 plus 1, we think about as a bit. So 1 plus 1 is like the 2-element set. You can be either the left element or the right element. Right? So 0 is sort of the one element, 1 is sort of the other element. So if we start the program here, I have 1 plus 1 times 2. I have 2 input bits. I'm going to distribute this into, 1 times 1 plus 1 times 1. On the first one, so that means if the control bit was sort of on the left, if it's 0, then you're going to go into this summoned. I'm not going to do anything. If the control bit here was on the right, so if it is set, you're going to go into this summoned. And in that case, I'm going to do the command that I wanted to on the bit that I wanted to. Right, so this is sort of a case split, if you like. And then we have to put the thing back together from here back to there to make the types match. So you can have for free some sort of control structure in your programming language. If you think about this bit 2, the 2-element set as as bits, then the swap, which is also one of my coherence isomorphisms. And that's why I put it in. There's a command you can give in this language. So the swap would be like the NOT gate. Right? If I swap the 0 and the 1 element, that's the NOT gate. So I can write stuff like control NOT. And I can write stuff like controlled, controlled not, all purely from the coherence isomorphisms. Just the structure of the category of this programming language lets me do that. And there's a theorem saying this Toffoli gate, this controlled, controlled not, any reversible function you can write that way. So now it's automatically computationally universal. Okay, so this is Pi, the programming language for working with permutations. It's a universal one for classical reversible computing. Now I have to say a bit about strictness. So far I've brushed under the rug that these coherence isomorphisms have to be coherent and have to be there, and they might not be identities. You can in fact pretend that they are. So from now on, I'm not going to talk about rig categories. I'm going to talk about groupoids. So all the maps are invertible. We want to be able to run things forward and backward. And in fact, every rig groupoid is rig equivalent to what's called a bipermutative category, where all these coherence isomorphisms are strict, except maybe for the swap. So you can do that. Second simplification I'm going to make is we can restrict ourselves to what's called semi-simple rig groupoids. So I don't want to talk about arbitrarily big sort of objects. I want every object to be a finite sum of ones, so sort of finite numbers, if you like. I don't want infinite types in my language. So semi-simple, which has a cool consequence that in some sense, the times doesn't matter at all anymore. You can reconstruct the times from the plus in these cases. You can distribute everything out. Every type will be a finite sum of things. And any function between two things I can distribute until I have a sum of simple things with no times inside. And then the tensor product you can sort of reconstruct as a sort of Kronecker formula, like you do for vector spaces. So semi-simple rig categories, and certainly semi-simple rig groupoids, are special cases of props. So they're nicely handled algebraically. They're just props with one extra property, that this Kronecker thing is bifunctorial. And the last thing I'm going to ask for today, I conjecture that you don't have to ask this, and we're working on that, but it's unclear, is that the rig categories that I'm going to talk about are cancellative, in the sense that if f plus g equals f prime plus g prime, they sort of cancel one of the two summons, and, oh, sorry, this should be f is f prime. As we're talking about groupoids, that's the same thing as saying if f plus identity equals g plus identity, then f must be equal to g. I should be able to sort of discard one part of a disjoint union. I'm going to be slightly coy about this. I think this is true in the models we're talking about, but I'm not exactly sure. Worst case, we can just build it in. We can force it. Okay, so that's about strictness. Now, this model for classical reversible computation, this programming language Pi, is fully abstract and adequate in the following sense. First, every finite computation, finite permutation, every possible classical reversible program you might want to write down, might want to compute, I can write in this language. And that's fairly easy to see because every permutation is a composition of transpositions where you just flip two elements at a time. All the transpositions I can build because I have the swap map and I have my bookkeeping maps, and hence I can build everything. And in fact, this language Pi is equationally fully abstract in the sense that you have semantics going from the sort of syntax to your favorite rig groupoid. Two pieces of syntax, two programs will be equal exactly if and only if they are equal in every interpretation in every rig groupoid. So specifically, it's good enough to look at the rig groupoid of sets and permutations, but you can take any one you like. And the final thing I want to add, and this is something we're currently working on with Louis, who is here today, so you can chat to him about this, is adding control to circuits. If I have some base prop or base algebraic theory about any kind of circuits you like, some monoidal category, you can add a plus to that in the sense of making it a rig category. And our claim is what this is doing to the sort of programming language of circuits is exactly adding controlled gates to that. So you can do, if you had something like a knot, now you can make something like a controlled knot. So this rig structure is really sort of the least you need to add and want to add if you want to talk about controlled things and classical reversible things. Good. Next piece, right on target. Third piece, I'm going to talk about what do we need to add to this classical reversible programming platform. I'll take Pi as sort of the such thing to make it quantum. So how do we complete this in some sense? I'm going to start with a quote by Dorit Aharonov, who has a nice picture over here. And she's one of the founders of, yeah, I think that's fair to say, of quantum computation. She's certainly a very big name in the field. And in some interview, she said, I won't read the whole thing, that quantum computation is some kind of completion of classical computation. And that's what I'm going to shoot for. So the way she thinks about it is it's similar to the fact that complex numbers are an algebraic closure of the real numbers. So let's unpack that. So by algebraic closure, she means that you have some field, it could be the real numbers. It's called algebraically closed if every polynomial has a root. Right? You can always solve any polynomial equation, apart from constant ones. So the real numbers are not algebraically closed. Right? There's a polynomial, x squared plus 1. There's no real number x that satisfies this. That makes this equal to 0. So if you want a solution to this kind of polynomial, you need to add something to the real numbers. Of course, we're going to add exactly the root of that polynomial, which will be I. And we get a new field, which is the complex field, which is algebraically closed in the sense that any polynomial now does have a solution. So you can complete the reals to the complexes, complete in the sense of I want to be able to solve polynomials by adding a single thing called I. So that's the kind of thing we're going to do. Instead of the reals, I'm going to talk about pi, right? Classical reversible computing. Instead of I, I'm going to do something similar, add some sort of square root. But in a sense, this is a bit too much. We don't need all of this real stuff. We are computer scientists, I guess. I am. I like discrete things. I like finite things. So I don't need all of these reals. I'm going to start just with everything I need and nothing more. So let's go back to just naturals. Not reals, just naturals. So if I want to add the ability, so naturals are a ring, right? A semi-ring. I can add them, I can multiply them. I cannot subtract them. If I want to be able to add this ability of subtracting, I need to add something to it. I need to extend them to the integers. And I can do this in several ways, right? The naturals sit inside the integers in several ways. I can send the number n to itself. I can send the number n to minus that thing. That's a fine homomorphism that still preserves addition and multiplication. Or I can send n to 2n. I can send n to 3n. There's many ways I could do this. The fact that z is a completion of n means that in some sense, these things are all the same, right? Up to isomorphism, in this case, an unimportant global scalar, you know, either a scalar 1 or a scalar -1 or a scalar 2 or 3 or 4 or whatever. And we don't care about these global scalars. These are all the same. The fact that it's a free completion, right, that this is the universal way of adding subtraction to naturals, means that any other way I could add subtraction to naturals has to factor through this. So the reals, of course, are also something that includes the naturals. There's also something where you can subtract. And it has to, so there's many maps, many addition preserving and multiplication preserving maps from n to r. They all have to factor through z. So the lesson to take from this, if we're going to play the same kind of game with classical reversible computing and quantum computing, is if we do this in a universal free way, then it doesn't really matter sort of how we do it as long as it's universal. They're all going to be the same. And conversely, and this is maybe more interesting, classical computation, at least classical reversible computation, sort of sits invariantly within quantum computation in any model we're talking about. So I can always sort of reconstruct classical computation from quantum computation. That's not so interesting, but there's only one way of doing that. That's the interesting part. Okay, so now I'm going to have to tell you about quantum computation. So instead of permutation matrices, we're going to be talking about unitary matrices with complex entries. So complex n by n matrices. You can multiply such things. You can take adjoints of such things, and that's what this dagger means. If F is an n by n matrix, then F dagger is the thing that's transposed and complex conjugated at a matrix a unitary, exactly when it's inverted by its own adjoint. So that's the kind of things a quantum computer can do to a qubit. So qubits are two-dimensional vectors. You can take tensor products of them to get 2 to the n dimensional states. And you can active them by 2 to the n by 2 to the n unitary matrices. The laws of physics tell us that this is the way you can act on quantum systems, and this is the way quantum programs should evolve. And they're a bit like numbers. You might remember this from a course in linear algebra or functional analysis. They behave a bit like complex numbers in the sense that you can take squares of them, you can add them, you can multiply them, you can take square roots of them, you can think about polynomials in them and they might have solutions or not. And for unitaries, it turns out that all these kinds of polynomials that we were interested in before, they always do have a solution. You can always take square roots. So the way you could do that is you diagonalize your unitary matrix and you take square roots of all the things on the diagonal. So basically it comes down to, again, the complex numbers being algebraically closed. Okay, good. So permutation matrices sit inside unitary matrices. It sort of extends classical reversible computing, but now we can take square roots. It's completed in some sense. So, of course, now what I'm going to tell you, I've been priming you for this the whole time, is this enough? So not all reversible classical programs have square roots, but all quantum programs do. Is this maybe the thing, if we add the ability to take square roots, does that take us from being able to do classical reversible computing to all of quantum computing? And the answer is, of course, yes, we can. Otherwise, I wouldn't be telling you this. So here's what I'm going to do. We're going to start with pi, like the basic universal classical reversible computing language. I'm going to add to that 2 generators. I'm going to force 3 equations on them. Generators are of this type, one called W or omega, that goes from type 1 to type 1. So type 1 is it's a weird kind of type, right? It's half a bit, if you like. So this is a bit like a scalar, a bit like a number. Second one I'm going to add is called V, and it goes from 1 plus 1 to 1 plus 1. So we were thinking about this as bits before. Now they're going to be qubits. I'm going to add 1 extra operation you could do on a qubit. What are the 3 equations we're going to I'm going to enforce on them? First one says that V squared is equal to swap. So swap was the NOT gate that turns 0 into 1 and 1 into 0. So I'm going to ask for a square root of the NOT gate. This was this permutation before that didn't have a square root, if you remember. I think it was green and orange that you swapped and you can't take a square root of. I'm going to just ask, please, let's formally adjoin freely a square root of the NOT gate. Second thing I'm going to ask is that this number here, the scalar, if I raise it to the power 8, I'm going to get the number 1. So I want an 8th root of unity. Later on, I'm going to be talking a bit about, depending on time, levels of precision and sort of this epsilon that I mentioned, how close you can get to things. This is sort of the real case of interest, but you could take higher powers of 2 and get sort of better efficiency, if you like. And then the third equation I'm going to add is this mysterious looking one that says VSV equals SVS, where S is something in terms of the number 1, the number omega. Okay, so I'm going to add 2 generators. I'm going to force 3 equations. Good, something you can do. Fine, this is a piece of syntax. But now, of course, I'm going to convince you this is the right thing to do. So where do these equations come from, first of all? I'm going to claim each 3 of these equations are doing something natural. First equation was the one that said V squared equals swap. So qubits you can think about, so bits we were thinking about as 2 element sets, right? They can be left or right, they can be 0 or 1. Qubits are often depicted as on this kind of block sphere. They can be vectored anywhere on the surface of a 2-dimensional sphere, in 3 space, where the bit 0 is sort of the North Pole and the bit 1 is kind of the South Pole. So the NOT gate is sort of turning this thing upside down. So what the V gate is doing, this V generator that I'm adding, it's a square root of NOT. It's sort of doing this rotation, but sort of stopping halfway. And there's many ways you can do that, right? You can stop here, you can stop there, you can stop there. In a sense, they're all the same, but I'm going to pick one. And this is borne out in how people actually build quantum computers in hardware. So Google has a device. One of the native operations is exactly this kind of square root of NOT thing. In optical quantum computation, so Google has a superconducting device. There's a native thing. You can build them in a different way, which is optical. It works with photons and lasers and mirrors and things. the way they build that is you have what's called a Hamiltonian. You let that evolve for a number of seconds t. And then it's very easy to do sort of a square root of this thing. You just let it evolve for half that time, or you shoot the laser at half the energy. And they literally, that's how they implement not case over there. So this first equation, that there is a square root of naught, makes total sense. The second equation I'm going to duck out of for now, and I might come back to later. It has to do with sort of constructivity and efficiency. This third equation that maybe looks more mysterious is I made a picture of it of Bloch spheres over here. If you sort of track what happens if you start at 0 and you do VSV, you sort of rotate here and then there and then there. Or you can do it the other way around. If I do SVS, I go there and then there and then there. You end up with the same vector, and this is always the case. One way of thinking about this is you might have heard about Euler decompositions if you work with any sort of computer graphics. So any rotation in 3 space, you can always specify in terms of, I think it's pitch and roll and yaw. So you can do that sort of in an X, in the XY plane, and then in the YZ plane, and then the XY plane again, or you can do it the other way around. That's basically what this equation is saying. These two decompositions into sort of standard angles are the same one. Another way of thinking about that is this equation SVS is VSV happens to be the generating equation for the 3-strand braid group. So if I think about pictures like this, or braids about 3 pieces of wire that can go over and under each other, they form a group. I can compose them and I can turn them upside down, and then I have an inverse. And this, if I take 2 generators, the one that swaps the left 2 wires, that's S, and the swaps the rightmost 2 wires, that's V. So I do SVS. That happens to be the same as VSV. And I can present this 3-strand braid group by having those 2 generators, that equation, and that's it. And that is how what's called anionic quantum computers are built. This is sort of the defining equation that makes them work. So my point is these 3 equations are not just random, they actually are implemented in hardware that way. That's sort of what makes them work. Okay. So that was our syntax. Now I better have some sort of semantics to back it up. Of course, I'm going to take some sort of rig groupoid as semantics, because then I, for free, get all this classical reversible goodness. And a model of this kind of semantic model for this kind of programming language needs to have 2 additional things to interpret these 2 generators, omega and V. They have to have the right types. And I'm just going to ask that they satisfy the same equations, which makes total sense in a rig category. Unitary matrices form such a model. Permutation matrices sit inside there, so I have all of that. I can interpret the 2 extra generators as this 8th root of unity, and this 2x2 matrix. And this happens to be a native gate in many quantum computers. And it is one of the square roots of the knot matrix. Okay, this is the main slide. If you forget everything else, I would like you to try and remember this. So we now have built some sort of programming language. I'll call it FREAK, for free quantum computing. I have a semantics for this, and the semantics is good because here's 5 arguments. First of all, this free thing exists. Right? This might be trivial, but you have to show that this model exists, that these equations are not contradictory. Fine, it exists, but it's some sort of formal syntax thing. What does it look like? Well, you can prove if I write D for dyadic rationals, so rational numbers, fractions of integers where I can allow powers of 2 but nothing else. I write zeta 2 for a root of unity. Then you can prove that this formal syntactic model is equivalent as a rig category to unitary matrices over this ring, where the entries are rationals with this square root of, root of unity and nothing else. So you don't need all of these complex numbers, you only need these. And this is discrete, is the point. I'm probably not going to have time, I saw, to talk much about this sort of precision level, but you can make a language pi k where this k is higher than 2. There's an inclusion of pi k into unitary matrices over the complex numbers this time. And if k is large enough, specifically when k is 2 already, this is dense. So in the sense that any complex unitary matrix I can approximate up to arbitrary precision with terms in FREAK, with programs. So I can make Any computation you might want to do up to any error margin, I can program in this language. This is sort of expressivity theorem. And these latter two I'll maybe skip over for now. You can sort of lower the precision level at the cost of one additional auxiliary qubit. And you can add measurement to this. I've not talked about that at all. We're only talking about the reversible part, but you can have a second universal formal construction that's totally natural and can be explained. So it adds just what you want and nothing else for measurement at the end of the computation. And you can prove that this does exactly the right thing. So that's great. We have a programming language, we have a semantics. And I want to skip a few things. I wanted to give you an idea of how this proof works. And maybe I'm going to do that like this. Yes. So one thing I want to emphasize about this model is everything is finite. There's a finite number of generators, a finite number of equations, which is new. All of the models that came before either have generators that are parameterized by real numbers, or have equations that are infinite families parameterized by real numbers, or have equations that have quantifiers with for all and exists in them. So something like this Euler decomposition about sines and cosines and things. Everything is finite. There's only finitely many generators, finitely many relations. Computers can deal with this. So specifically, I can automate all these kinds of proofs about rewriting quantum programs into other quantum programs. Here's a simple example that shows if I do the S gate twice, I get what's called the Z gate. And I'm not going to step you through it, but if you were to inspect this, you would see that each of the steps is simply some sort of either a coherence from rig category land or one of the three equations, three axioms. And you can formalize all of that kind of thing in ACTA. Skip this too. No, I'm going to give you this as the last example and then I'll stop. So you can make this slightly easier on yourself. Now we had two generators and three equations. I can even take this down to one generator. Price to pay is that this generator now doesn't have like a physical interpretation so much anymore, but it does make reasoning a bit easier. So instead of the V and the W, I can take what's called the Hadamard gate as a primitive. So I take all the stuff from pi and I add another gate from qubits to qubits. It's called Hadamard. And I'm going to ask that it satisfies these three equations. So these are string diagrams, but with the caveat that they're in the monodal category for the plus, not the times. So these wires are dimensions now. They're not qubits. So doing this thing twice is the same as doing nothing. You're doing H, not H. You can sort of swap these two things around. And this is sort of cancellativity I'm building in. This is still same kinds of proofs. They're still complete and universal and everything. But the way to prove that is a bit ugly because we have to resort to matrices at the end of the day anyway. In the course of the proof, we found a new finite presentation for the orthogonal groups, right? So orthogonal matrices with entries in this here ring, where you have generators like XAB that sort of swap the A's column and the B's row and column. Generators like -1 that are diagonal 1, 1, 1, 1, 1, except for a -1 on row and column B. And generators like HAB, which are sort of like the Hadamard gate, except on row and column A and B. So it's a bit ugly. You can drive all of these rules about them, and they are a bit ugly. But if you do a lot of work, this is a finite presentation, and you can reason with it. And so here are some things you can get that way. So we were talking about these controlled kind of C1 gates. So this is a 2-qubit gate. It's a linear extension of the thing that if the first qubit is 1, then it does C1 on the second. If the first qubit is 0, it does nothing. So if I do a controlled C1 and then a controlled C2, that's the same thing as doing a controlled composed C1, C2, as you would expect. Same kind of way, if I have a positively controlled C1 and then a negatively controlled C2, so this one does C1 if that is set, this one does C2 if that is not set, these two things are going to commute. If I do a positively controlled and then a negatively controlled, that's the same as just forgetting about the control and doing the thing anyway. And this one is maybe a bit more intricate, but the point is all of these kinds of simple circuit equations follow directly from the rig coherence laws and the axioms. So these are simple ones. And then you can go and implement this and automatically reason about certain things. Here's a quantum circuit. Nobody knows what it does, but you can just start to normalize this kind of thing. I'm just going to flash this at you because there's no point doing this now. This is one of the rules, turning it into that. And then this, and then that. So all of these are simple rig coherences or axioms. And then you can start to simplify stuff. At the end of the day, it's just that. So this way we can automatically not only program quantum computations, but optimize them as well. And we can try and build this into some sort of compiler. Okay, I've told you all I wanted to. Let me conclude. What have I told you? I've presented Freak, which is a universal quantum programming language between square quotes, because this is still kind of low level and we're looking for the right primitive constructs, like the higher level things like while loops and recursion and things. But it is computationally universal, fully abstract, equational, sounding complete, and very simple, right? 2 generators, 3 equations, nothing else. What do we want to do with this? I want to build this out into a fully fledged, surface level syntax, so that I didn't talk about these measurements, but I want a nice syntax that brings everything together and actually people can write, freak programs. Because then you can think about what are the right primitives. And Kim, for example, is working on finding sort of recursion schemes that do work in this sort of quantum setting. I want to write, and we're busy doing this. Malin is sort of writing quantum error correction algorithms in this kind of language, seeing what they look like. And if I'm very brave, we would like to discover new algorithms. So we have a sort of more powerful way of writing things down. We could either automatically explore or try and reason with our human brains, what else could we build this way? We're busy writing a compiler for this and having intermediate representations. One problem there is it has to be efficient because circuits are sort of n bits, but the matrices underlying them are 2 to the n by 2 to the n. You have to prevent going through the matrices. So you really need to work with this free syntax and not sort of the underlying models. And you can have sort of automated logic in ACTA. And then I'm going to thank you for your attention and leave you with some references.